So, welcome student to the new class of this Introduction to Nonlinear Optics and in Application course. Today lecture number 24. In the previous class we have started a very important concept called Newman's principle. The Newman's principle suggests that if I put some kind of symmetry operation on a crystal in terms of its susceptibility, which is a tensor, that will going to change under this symmetry operation. But since the operation is symmetric in nature, whatever the D matrix or susceptibility matrix we will going to find after putting this kind of operation, they are same that of the before. So, before symmetry operation, whatever the D matrix we will have, after applying this operation we will going to have the same D matrix if my operation is symmetry in nature. Symmetry related to that related crystals. So, let us again try to find out, because the Newman's principle we just state the thing, but we never show any kind of application of that. So, today we will going to show some application on that, and then we will find a very interesting application of Newman's principle and find that centrosymmetric system where we have a center of symmetry, how the susceptibility tensor will going to change for that, and eventually we find that the second order tensor or the second order susceptibility or the second order nonlinearity will not be there. That means, it will going to vanish in case of centrosymmetry. This is a classical example of Newman's principle. So, okay, so let us continue with the Newman's principle what we have. So, as the slide suggests that in Newman's principle, the susceptibility tensor of the material belonging to a certain crystal class must be invariant under corresponding point group. That means, if I rotate or if I change this put some kind of symmetry operation, the D matrix will remain invariant. So, now here once again let us understand this equation which is written here, looking very simple equation, that D I j k is the I j kth component of D matrix under symmetry operation, and if I put some kind of symmetry operation like changing the coordinate system. So, this new coordinate system, the D matrix has a prime on over that. So, this is a under prime coordinate system. Say this is a non prime coordinate system and this is a prime coordinate system. If this is x, y, z, this is the principal axis, say suppose, and this new one is big X, big Y and big Z, which is a prime coordinate system, or if I put some kind of prime, it will be easier for you to understand. So, in this coordinate system, in the red one, the D matrix, the form of the D matrix will change, like the component of the vector change. In here, if I have a vector here, the component will going to change if I rotate my coordinate system. In terms of vector, also in terms of if I in place of vector, if I use say some sort of matrix or tensor, then the tensor components also going to change under this rotation or this kind of symmetry operation. So, if I put this operation over a matrix, then the relationship between the old and new matrix will be represented by this particular form, as it is shown, that I j k component is represented by alpha, beta, gamma, and this alpha, beta, gamma is a repeated one. So, that means, if I put a summation sign over that, it should be over alpha, beta, gamma. So, alpha, beta, gamma will going to change. So, in order to have one specific component in D I j k, we will have to make a sum over alpha, beta, gamma, and all the cases we need to find out what is my R j R 1 R I alpha, R j beta and R k gamma, and then only we can able to find out what is my I j k. Now, if my operation is symmetric in nature, then after doing everything, whatever we will get as D I j k prime, it should be the same value that we start with, that is, it should be equal to D I j k, because eventually after applying the symmetry operation these things will not going to change. So, we will eventually have the same value of D matrix. So, this basically gives us an additional information through which we can find out what should be our D matrix components. So, let us now go to our next slide. Okay. So, this is the old, again this is the old slide where we will now say that my whatever the matrix we are going to use as a transformation matrix, rotation matrix, or in general operation matrix, this is symmetric in nature. That means if I use this matrix component to find out what is my new susceptibility components. So, this operation is symmetric, but the operation rule is again the same thing. So, these are the operation rule and this is my total matrix. So, this is the structure. I have given R, I have given D, I am going to apply over that. So, my goal here is to find out the prime. So, if I want to find out, it should be D 1 1 prime, D 1 2 prime and so on. So, what is the relationship between D 1 1 and D 1 1 prime? I can figure out with this R. So, for one component there will be several number of terms are appearing because it will be alpha, beta, gamma. So, alpha, beta, gamma is the running index or Dam indices. So, it will going to run from 1 to 3. So, there will be in principle many terms there, and it depends on how the symmetry operation or the symmetry matrix will look like. So, let us take this example so that you can understand exactly what I am trying to say. So, suppose we have a crystal which belonging to the crystal class C4, and that means it is invariant under the rotation of 90 degree about x3 axis. So, we have a axis, and if I rotate this axis, so we have a coordinate system. So, suppose we have a x, y, z coordinate system, x, y and z, and if x, y, z is represented here x1, x2 and x3, this is basically x1, this is basically x2 and x3. So, if I rotate these things to 90 degree or pi by 2, then whatever the crystal we have, this since it is a symmetry operation, we will have the same crystal again. So, first we need to find out, once the operation is given to us, then first we need to find out what is my R here. That means, we need to first find out the symmetry operation matrix. So, here we can see, since we are rotating 90 degree, so my R matrix will be simply 0 1 0 minus 1 0 0 0 0 1, because rotation matrix we know it was cos theta, sin theta 0, minus of sin theta, cos theta 0 and 0 0 1. This is the rotation matrix around z. So, sin theta means sin 90 degree, it should be 1. So, this negative sign give me minus 1 here, sin theta here also we have 1 1, and cos 90 degree 0, and this 1 is there. So, eventually we will have a matrix R here. One thing you should note that most of these elements are 0 here, only 3 elements are there in R matrix which are non-zero, R 1 2, R 2 1 and R 3 3. So, these are the terms that will going to affect on this rotation thing or this operation thing, but other things will not going to, since it is 0, it will not going to play any role. So, the aim here is to, if a D matrix is given like this, we need to find out the transformation of these coefficients. So, now you can see that there are only 10 different coefficients are there. So, if you able to find out after transformation what should be my coefficient, So, we just need to find out these 10 independent coefficients, because others are the same values. So, once we know these 10 independent coefficients, I can make, after the rotation operation, whatever the new matrix we have, we know that this and old matrix will be same, then we will try to find out a one-to-one correspondence between them and eventually independent values of this. So, let us see how we can do that. So, R is given to us. So, R is given to us and D matrix is also given to us. So, let us start the operation. So, one by one we will going to do. So, this is my main equation for transformation on the left hand side. R is given, where these are the non-zero elements that we have written explicitly, that it should be R11, R21 and all these things. Now, what we will do? We will try to find out, first we will try to find out what is my D prime 11. This is the first element. D prime 11 is nothing but D prime 111, because I need to use the extended form, not the contracted form, because 3 coefficients are there. So, once we write D 111, so I need to write R1 here, R1 here, R1 here. So, let me give you the idea how to do that. So, I need to find out, this is my rule. So, I need to find out 111 prime. So, this is my rule. The rule suggests ijk is 111. So, R1 is should be here, R1 should be here, R1 should be here, and D alpha beta gamma will be there. I do not know what will be the alpha beta gamma, but if you look very carefully, whatever the value you put except 2, you will get 0 always, because only R12 is 1. So, if I write 1 here, then this value has to be 2. If you put 1, then R11 is 0. So, entire multiplication will go to 0. For non-zero elements, I am just writing what should be the non-zero elements here. So, you have to put R2 here. In the same way, since it is 1, you have to put R2 here and 2 here, so that you have a non-zero elements here. All the other elements will going to vanish once you find D111. So, if I put 2, 2, 2 here, so automatically my choice of alpha, beta and gamma will be 2, 2, 2. So, this is essentially the equation that we have. So, we find that D222 is nothing but D11 prime, or D11 prime is equal to D22. That is my first coefficient, and this coefficient D11 prime can be represented in terms of D22, which is a non-prime coefficient. Okay. Now, next, what should be the value of D22, D122? The next one is D12. So, D12 prime is D122 prime. Now, we know that D prime 122 means I have to put R1 here, R2 here and R2 here, because I j k here is 1 2 2. So, I is equal to 1, j is equal to 2, k is equal to 2. Again we find that if as soon as I put R1 here, only for non-zero components if I want to find, I need to put R2, because R12 is only 1, other terms are 0. When I put R2 here, then we find that 2 1 is a component which is non-zero. So, I have to put 1 1 here, and here again I need to put R2 1 here. So, that here this 2 1 1 I put like this. So, see this expression, in the expression I am essentially writing the same thing. Now, R11, R12, R21, R21, this is 1, this is minus 1 and this is minus 1. If I multiply it, it should be 1. So, eventually we have D211 is equal to, eventually we have from this we have D12 prime is D16. So, you can see that even after finding 10 independent components, these 10 independent components again they are equal to each other. So, D21 and D16 there we know that they should be equal and we are getting the same thing once again. Now, what happened to D133, the next term? So, again in the similar way we have to put R1, 3 and 3 here. So, R33 is non-zero. So, I need to put 3 here and once I put R1 I need to put 2. So, that we have a non-zero elements here and all the other elements if you calculate meticulously. So, you will find that all the other elements will be 0 because of these R matrix components. So, now D233 you need to put. So, from here we can find that D13 prime is essentially D23 in non-prime system. So, in the similar way we find D123 which is this, D13 which is this and so on. So, how many components we figure out here, independent components? We know that in the previous slides, so we have already mentioned that how many components we need to calculate. So, we need to calculate D11, D12, D13, D14, D15, D16, then D22, then D23, D24. So, 10 independent components we need to find out and we start with D11, D22, D33. So, let us see in the next slide how many components we figure out in non-prime and what is the relationship between these two from prime frame to non-prime frame. So, how many components here we find? This is one component, this is second component, this is third component, this is fourth component, this is fifth component, this is sixth component. So, 6 different components we figure out. Again there are 4 different components still remaining, but we will going to use the similar procedure to figure out of these 6. So, let us see whether we can find out these 6 or not. Yeah, these are the next 4 components and again we will use the same thing. So, let me do that once again. For example, any arbitrary component if I want to find out say D233. So, D prime 2 3 these components if I like to find it will be D233. So, D prime 2 3 3 if I put the R value I need to put R2 here, R3 here, R3 here and D, and here R2 3 3 once I put then I have to put R1 here, R3 here and R3 here. Once I put we will find that here I need to put 1 3 3. So, D23 is essentially minus of D13. So, this from this one thing we can find that they are related to, because after making the transformation whatever the D matrix you will get that should be exactly equal to the previous one. So, that means this component, if this component is minus of this component then there should be some relationship. So, we will find what is the relationship. So, let me do that. So, we figure out in these last 2 slides we figure out all 10 independent components in prime frame or after operating the symmetry operation onto the system what should be the form of the D matrix we figure out. Well, so let us now try to find out what is going on. So, these are the entire list of whatever the values we figure out and that is important. So, after figure out all the components, so D11 is related to non-prime, so D22, D12 is related to 16 and so on. But here one thing you should note that D11 prime and D11 they has to be the same value, because I am applying the symmetry operation. Once I am applying the symmetry operation my Newman's principle is valid, and Newman's principle suggests that if you apply the symmetry operation then the new component which is prime component should be equal to the old one. So, D prime 11 should be equal to D11, D prime 12 should be equal to D12, D prime 13 should be equal to 13 and so on. So, that means we will have a relationship between that these two D11 and D22 should be equal, D12 and D1416 should be equal, D13, D23 should be equal. So, we have these conditions. So, now from here we find some kind of interesting expressions that is really interesting. So, here D11 we find one equation is D22. In the similar way we find D22 is equal to D minus 11. So, if I compare these two equations, we will readily find, if I now compare these two things, we find D11 is equal to minus D1, this has to be this. Now, it is never possible that D11 equal to D minus of 11, that means D11 has to be 0. Once we know D11, only solution of this equation is D11 is 0. So, D11 is 0 means D22 is 0 because D11 and D22 0. So, you can see that applying Newman's principle, we can find out exactly what is the value of D matrix, what is the value of D matrix, and find there are many zeros in D matrix. So, D11, D22 is 0, that we find. Okay. What else? Let us see this equation, D16 and D12 are same. Here we find another equation D16 and D12, but they are related with a negative sign. Now, from this equation, these and this equation, we can readily say that D12 and D16 has to be 0, otherwise these two equations cannot be satisfied simultaneously. What else? We can find that D13 and D23, and again here D23 and minus of D13. If I again compare these two things like the previous cases, we find that this has to be 0, D13 equal to 0 or D23 equal to 0, and that is the only solution for these two given equation. So, again we find these twos are 0. What about D14? We have a equation here where it suggests that D14 is equal to minus of D14. Again this equation cannot be possible unless the value of D14 is 0. So, that means D14 value is 0. Anything else? D14, okay, we have one equation D15 is equal to D24, but we do not have any other equation. So, that means D15 and D24 for this symmetry operations are same, or the D elements, the matrix elements on D is same for these two, for D15 and D14 are 2. Apart from that, there are other equation which is consistent, that D33 is D33, that is fine, no problem in that. So, we have almost all the equation in our hand. Here also we have D24 and D25. So, these two equations suggest we can't find any explicit value of D15. We just have a relationship, and this relationship suggests that D15 and D24 is same. So, once we have all this information, so all the values of D11, D12 is known to us. We started with these D values, these are our starting point. So, once we have these values in our hand, so next thing we apply the symmetry operation, and when I apply the symmetry operation, we find that these values are zeros and there is a relationship this. So, from this we will have finally this expression of D matrix, and this expression suggests that D11 is 0, this is 0, this is 0, this is 0, D15 which is not equal to 0, I put this 15, 16 again 0, from here we can write all these other terms are 0, D15 I should write here because D24 and D15 are same. So, these two are the same elements, then 0 0, D15 is here, D15 is here, this is already because in this operation it is already there, and then D33 is one independent coefficient that is sitting here. So, eventually how many independent coefficients are there in D matrix? We started with 27, then reduce it to 18, then we reduce it to 10 up, and now after applying Newman's principle we reduce it to 2. that is I think a significant reduction of the coefficients, and now we find that we have only two components which are independent to each other, and this symmetry operation basically gives us the idea that how one can find the D matrix, different D matrix. Well, let me finally tell this centrosymmetric system what is going on. So, in crystallography we have some kind of system which is centrosymmetric in nature. In centrosymmetry, what happened, the crystal have a center of symmetry. So, that means if I change the point x y z to minus x minus y minus z, so the material should be indistinguishable. That means there is a center of symmetry here somewhere. So, we have this center of symmetry, around this center of symmetry we have this some kind of indistinguishable point here. So, the once I go from minus x y z to minus x minus y minus z, my matrix here will going to change. Okay, let me go back to previous slide. So, this is the matrix, the operation matrix form. So, R, it is very important that first we know what is my R matrix. So, R matrix should have this kind of form, that minus 1 0 0 0 minus 1 0 and 0 0 minus 1. So, this is the form of the R matrix. So, once we have the R matrix in our hand, then the next thing is to find out for this operation what should be the new elements. We will going to use exactly the same expression that we are going to use for last few classes or last few slides, and that is this. So, susceptibility, second order susceptibility will be represented in this way. But here one important thing we should note, that this operation matrix is diagonal in nature. So, R I j is essentially delta I j with a negative sign. That means R 1 2, R 1 3, it will be 0, only R 1 1 is not equal to 0, and this R 1 1 value is minus 1. In the similar way, R 2 1, R 2 3 are 0 and R 2 2 is minus 1. So, if I now write this thing, we will find important information. So, one important information, this is the chi I j. Chi I j is this is the second order susceptibility. Chi I j is the second order susceptibility or the first order susceptibility rather. So, first order susceptibility, if I apply this R operator on this first order susceptibility, we find that it should be I j, there are two components. So, it should be R I alpha, R j beta and this alpha beta. So, once we have this relationship in our hand and then we put this delta operator, then we find that it will be minus 1 and it is 1. So, I j and I j are same. So, that means there is no change for centrosymmetric system, there is no change. If I apply the symmetry operation, there is no change of first order susceptibility. The first order susceptibility remain conserved, but what about the second order susceptibility? Second order susceptibility is more important here. So, I j k component will be there because it is a second order susceptibility and they are related to alpha, beta, gamma and alpha, beta, gamma. So, summation over alpha, beta, gamma. But this alpha, beta, gamma, if I go on to have different values, all the values will be 0, only these delta function values suggest that only the delta I, delta J and delta K will give you something, otherwise all the contribution is 0. So, if we do these things, we will find that susceptibility I j k is equal to susceptibility j I j k with a negative sign, and this is true for all the I j k's. And this suggests a very important expression that susceptibility I j k for all the I j k's is 0. So, the susceptibility value I j k was second order susceptibility 0 under this centrosymmetric system suggests that for centrosymmetric system there is no second order susceptibility. So, second order susceptibility will be 0 or second order susceptibility will vanish for centrosymmetric system. Well, this is the thing we like to we like to discuss in today's class. So, we will going to end here. So, in the next class we will start from more important applications, and today we find a very important thing that under symmetry operation, the structure of the D matrix will not remain change, it will be same thing that before the symmetry operation, and from that we can reduce the different components of the D matrix. And also for centrosymmetric system, if I apply the Newman's principle, we will find that the second order susceptibility going to vanish, and that is a very important and classical example of the symmetry operation. And in the next classes we will find more on these things, and with this note let me conclude here. So, see you in the next class. Thank you for your attention.